Good afternoon, Dr. Theo. So once again, I'm Ravi. I teach philosophy and literature at the School of Liberal Arts, and we are very glad to have Dr. Théo Le Bret here. He's a researcher in astrophysics. He did his PhD in Oxford on what he has just asked me to describe as on the research on dark matter in galaxies. The reason I say that is because we're actually going to talk more on that. So that was just a brief to me. And I thought we should right away jump in with this fascinating idea of what dark matter is, because just now when we were speaking before this podcast, as you said, there are some people who dedicate themselves to researching whether dark matter exists and how you have presumed the existence of dark matter and then gone ahead with your calculation. So if you could develop that.
So very quickly, just maybe a quick reminder of what dark matter is, like what we mean by that, right? Is that essentially the sort of world around us, the world that we see, is constituted of particles that are known as baryons, and they're visible, right? They interact with light. This is why you see things, right? So stars are visible. Planets are visible. All of this is made of regular baryonic matter. But over the last half century or so, maybe a little bit longer actually now, we've become aware that visible matter does not explain a number of things. Like that essentially, if we want to explain, for instance, the way that distant stars move around the galaxy, the way that galaxy clusters evolve or are in equilibrium, in order to explain these data, we need to include a new component, right, to our description of the universe, and this component is known as dark matter. So basically, dark matter is one of those words like dark energy, or where essentially we're admitting that we don't know what it is, we just know what it isn't, right? So we know that it's dark, so it doesn't interact with light, with electromagnetic radiation in the way ordinary matter does, and that's all we know about it, right? We know that it has no interaction with light, and we know that it has mass because it interacts with the gravitation. It interacts gravitationally, right? So just for a bit of history, the way precisely we discovered dark matter is that we were looking at the way that stars move around the distant outer edges of a galaxy, and we realized that in order to explain the motion of these stars, there had to be some missing matter, right? There had to be some matter that we couldn't see that really explained the movement of these stars. So essentially, yes, there are different ways of looking at the problem, I think. Some people, which was not my field, right? Some people are looking at the nature of dark matter, right? What kind of particles could explain dark matter, right? Are we looking at just large objects that just happen not to be luminous? Are we looking at black holes? This is a sort of like fringe theory, but it exists. Or are we looking at microscopic particles which we just haven't discovered yet in our experiments in, for instance, the Large Hadron Collider, things like that. And what I was doing was, assuming the existence of dark matter and just modeling how it will interact with the galaxy, right? So the idea is that dark matter is even simpler to model than the visible matter, because we know that it interacts only through one thing, which is gravity. So if you have a lump of dark matter, it will interact with visible matter and with other dark matter in only one way, which is by attracting it gravitationally, which means that it's sort of like a privileged area of study for the use of computer simulations, right? Because ultimately what we can do is just spread around some digital stars, put some dark matter around it, put all this in a computer and see how this evolves, right? Which is pretty much what I was doing my research on. And the open question, right, was how does the visible and non-visible part of the galaxy interact, right? In particular, for instance, we think that the dark matter is distributed in a kind of halo around galaxies such as the Milky Way. So the Milky Way roughly is a sort of disk. It has a few spiral arms. The disk is sort of a few kiloparsecs, as we say, large, and beyond it, about 70% of the mass of the galaxy is contained in a large diffuse halo, which extends for hundreds of kiloparsecs around the galaxy. And the question was, well, okay, so we've got all this mass. It doesn't interact with light. We can't actually see it. But we know that it is going to interact with the stars via gravitation, at least. And so the question was, given that, given all the movement of a galaxy, movement spins around on its axis, it's got a galactic bar which moves around, it can also collide with other galaxies. Well, the question is, okay, what happens to the dark matter in all of these events, right? And that's what I was really studying, sort of trying to figure out how the distribution of dark matter can bear an imprint of the history and the evolution of a galaxy.
Yeah. Dr. Théo, one of the things that we were discussing the other day is, the highly, when we do astrophysics, for many people who are not in science, they have this distinction between the sciences and the engineering, and that's certainly the case in India, where the image of science is either Galileo dropping stuff from the Tower of Pisa, or people in the chemistry lab, clinking bottles of, beakers of experiments, and or you have people in biology labs opening up frogs. But the whole idea that with the evolution of technology, the extremely, sophisticated nature of experiments, of observations, and studying observations and analyzing them has become that much more complicated. So from your own experience, can you give us a sense of how much engineering astrophysics requires?
Well, I think there are several ways in which, right, the distinction between the fundamental and applied sciences tends to blur a little bit, right? I think even for theoreticians, right, these days it's quite rare to be a pen and paper physicist, basically. There are very few actual living researchers now whose work primarily goes through just writing down equations and trying to solve them by hand, right? Most of the work that goes around tends to rely to some degree on computer simulations, computer analysis. And so I think everyone in physics, even theoretical physics, has to gain some understanding of software engineering, basically. We're all, and unfortunately, we're not really necessarily taught how to do it. So sometimes we're very bad software engineers, but we are, to some degree, software engineers, right?
Yeah.
And I think in the same way, there are many interactions between, and it's especially true of astronomy, actually. There is an enormous amount of interaction with the people designing the actual, telescopes or the satellites that we'll be sending out into space to gather the data, because ultimately this is a task that an engineer can't do on his own, because the task is so specialized, right, that it requires permanent input from the people who will be using the system, right? So no observational astronomer can afford to be entirely without some working knowledge of how his telescope works, right? And that's something which I think is quite key. And I think in general, from what you were describing, this distinction, this kind of very strict distinction between the path of a scientist and the path of an engineer, I don't think really holds so much at least in France and the UK, which are the two countries whose education systems I'm familiar with, right? In that it's not at all unusual for a physics student to then go into a field that is much more applied. There's a kind of like transdisciplinarity, which is quite noticeable. I think one of my old undergraduate friends is now was working with artificial neural networks and applying that to actually biology, right? Trying to figure out how the brain works, right? So there's a multidisciplinarity, I think, that does blur the edges a little bit between what is a strictly engineering problem and what's a more abstract scientific problem, I think.
Yeah, and sort of in some sense that leads me to the next curiosity that I have, because I'm trying to grapple with the kind of absurdity an astrophysicist must deal with, because here he or she is thinking about phenomena many light years away, and there's only so many ways of gathering information through instruments about it, and then you analyze it, and as you say, then you build models and simulations with all those presumptions loaded with all those hypotheses, and then you let the simulation acquire its own life, right? And you sort of want to believe that this simulation is truly saying substantive about something so many light years away, despite all the hypotheses, the presumptions, the idealization. So, can you talk a little bit more about that aspect?
Yeah, I think so. Simulation is really something that I've dealt with a bit, right? And this is, basically, the real question that keeps that I kept asking myself is, why are we simulating these systems, right? Because ultimately, if you just want to reproduce their behavior, right? If the mark of a good simulation is that it just does the same thing as the observable universe, then obviously the answer is, well, why not just observe the universe directly, right? There's a famous story, right, about the Chinese emperor who wanted to know his country and asked some brilliant map maker to make him a map. And the map maker makes him a beautiful map, 1/100,000th the size of his country, and the emperor is like, well, fine, but I still don't understand my country. There are too many details that you've forgotten in this map. So the poor map maker goes away, does another map, 1/10,000th. Guess what happens? The king says, well, still not enough detail. I want to know more. Give me a better map, a more detailed map. And so the map maker goes back, third time, with a 1,000th map, and the emperor is still not happy. So eventually the map maker just, he cracks, he snaps. And so he takes the king, says, here's your map, and just like walks him out of the palace and shows him the street. And ultimately I think there's a kind of like lesson to be learned for people who do simulations, which is that if we want to gain understanding about the universe, we do need to accept that our model is not going to capture everything, right? Because if we want to be able to test some very, well-bounded hypotheses, then it's not obvious that a very elaborate simulation that has incredible richness, that displays an incredible richness of phenomena and behaviors, it's not clear that simulation is the best adapted actually to our task. And also there's the additional problem, right, which is that obviously simulations are just models and they're computer models of reality, which means that they suffer from all kinds of artifacts that occur only because you've put the numbers in a computer, right? And this is particularly true in astrophysics, where quite often it will be no trivial task to assess whether something interesting that you see in the simulation is the result of the simulation working properly or the result of simulation artifacts, right? And that was something that I kind of grappled with a bit in my research, I think, and which led me, I think, in my own personal preference has been more towards more kind of like simple thought experiments, right, or simple simulation experiments, but which try to capture a very limited number of phenomena, so you can be more certain of what it is you're saying, I think, in those with these more simple simulations.
Yeah, in fact, I think that's, in some sense, what you're saying is even a contemporary astrophysicist would truly appreciate the genius of Kepler for whatever he did, because after all, he did manage to reduce the solar system into a manageable complexity and get some information.
Well, I think this is ultimately this is the aim of any scientist, right? Is we wish to make sense of complicated systems with as few rules as possible, right? There's very straightforwardly, if you have if one explanation requires 10 different equations and another explanation requires one, then we tend to have a very strong preference for the second option. And I think this is and I think this is something which occasionally, like in astrophysics as it's practiced now, there's basically computer simulations have become so ubiquitous that there's always a tendency, I feel, to not take the time to sit down with the equations, just ask the computer, right? It's like, for instance, we ask ourselves, what is the role of supernova feedback into in the evolution of galaxies? And and the answer would be, well, just put some supernovas in the simulation, add that component, and we can see what happens. And ultimately, like, a lot of very interesting things are happening with this, but at least to my mind, that wasn't something that. I quite liked the idea of using just very simple models to gain insight and gain intuition into things, right? I feel it's nice to have a more intuitive grasp of what's going on in your model, where sometimes the model can be as complex as reality, and that's sort of a drawback in some ways.
Yeah, I think we'll conclude with this one question which sort of makes us confront the complexity of astrophysics as it's practiced today, because I get the sense that when we are studying a phenomenon that is so far away, there's also this possibility that the very molecules those very stars at a molecular level have a different structure, or it's almost, what I try to say is that a very sub-microscopic, sub-quantum level phenomenon probably has an implication for an astrophysical phenomenon. So I mean, is that a complexity that you confront, that it's not like studying a toy model of objects on Earth?
So I think I think what you're talking about has there are different layers to that question, right? I think the first layer, which is very interesting, is that yes, astrophysics and cosmology in particular is the science of huge objects, right?
Yeah.
Objects roughly the size of the universe, or
exactly.
flashes of the universe.
Yeah.
And but the problem is that it actually, all of the processes that happen at this very large scale can in fact involve so the physics of microscopic systems. So, for instance, if you're studying dark matter dynamics, then the question of what dark matter actually is will be pretty crucial, right? Because ultimately, depending on what kind of form you assume dark matter to take, it just won't have quite the same types of interactions, right, with ordinary matter or with itself. And that's something that is still very much an open question, right, in physics. And I think it's kind of the thing that I enjoyed about astrophysics. It's a sort of jack of all trades thing, where you do a little bit of pure analytical mechanics, a little bit of gas dynamics, a little bit of hydrodynamics. There's just a lot of and indeed the issue is quite often that the phenomena we are interested in, they operate on all kinds of different scales, right? And it's not always obvious which scale you're allowed to neglect in order to correctly describe the behavior you want to explain. And I think the other thing that you were mentioning, right, the difficulty of sort of experimenting with the one universe we have, I think that's a very deep problem in cosmology, right? Because ultimately, we only have one universe. We don't run experiments with it. We can observe different patches of it, but ultimately this is not something. This is not a lab experiment, right? And I think there aren't that many branches of the natural sciences that have this problem of having access. And actually, it's not even just having access to just one universe, but it's one universe viewed from one planet, really. Yeah. Because we've never observed anything from beyond the solar system.
Yeah.
So one universe observed from one planet at one point in time, right? Because again, we can, as we look further into the far reaches of the universe, we also look backwards, right, in time. But nonetheless, we only have one viewpoint, right? There's no. We're very much limited by our own, what's known as our cosmological horizon, right? And I think that's an issue that is a long-standing problem, I think, for cosmologists, because how you can generalize from a system of which only one example it's complicated, right?
Yeah. So thanks a lot, Theo, for that. And as much as our cosmological horizons are limited, I think you have reasonably broadened our horizons about astrophysics and everything. So thank you again. It was a pleasure to have you.
Yeah, brilliant. Thanks for having me.
Thanks.